Good day everyone! In this video, we will be talking about the processor and its organization. Now that we already know the two main components of the processor, let us now talk about the components of its data path. First, the register. What is a register? A register is a hardware device used to store a variety of data, such as the addresses, program counters, and other data necessary for program execution. The elaborate discussion of the register will be on the next topic, so now let's proceed to the ALU, or the arithmetic logic unit. The ALU carries out the logic operations such as comparisons and carries out the arithmetic operations such as add and multiplication. The ALU has two input data and one output. Its operation affects bits in the status register, and it is controlled by signals from the control unit. So the next is the bus. Bus is a set of wires that acts as a shared common data path to connect subsystems within a system. It can be used only one at a time by one device, such as the register, the clock, or etc. A bus can be a point-to-point or a common pathway. Each device that uses the bus can be a master or slave, wherein the master initiates the action and the slave responds to the master's request. The next is the clock. The clock regulates how quick instructions can be executed and synchronizes all of the components in the system. It also sets the pace for everything that happens in the system. And now let's proceed to the control unit. The control unit serves as the policeman or the traffic manager of the CPU. It monitors the execution and transfer of all instructions and informations. It extracts instructions from memory, decodes these, and makes sure data are in the right place and at the right time. It tells the ALU which register to use and turns on correctly circuitry in the ALU for execution. It uses a program counter register to find next instruction, and it uses status register to keep track of overflows, carries, borrows, and the like.
All computers have CPU and can be divided into two parts. The first is the data path. Which is registers. The ALU or arithmetic and logic units. Connected by buses. Or the timing is controlled by the clocks. Together, these components performs the task of the CPU, which is fetching operations, decoding, and performing.
The instruction cycle. Evaluate operand address, trace, and execute. Computes the address of the memory location of the instruction operand, then performs the function of the instruction. If arithmetic or logic instruction, utilize the ALU circuits to carry out the operation on data registers. This is the only stage of the instruction cycle that is useful from the perspective of the end user. So the first thing it will do will evaluate the operand it will use. The first thing it will do will evaluate the operand that will be used by the program after After that, it will execute the phase and the logic instruction. It will evaluate the operand of the arithmetic logic units. Then it will execute the program. I'm done.
So let's move on about the instruction cycle. So what is the instruction cycle? It's talk about the instruction under the direction of a step-by-step procedure. So let's talk the execution cycle within this. So first is the fetch instruction cycle. The fetch instruction cycle. It is the instruction from memory then loads the instruction itself into the instruction of the register. The MAR or the memory address registered instruct itself then load to the MDR or memory data registered. It increments processor counter program counter the updates the instruction from the memory. So here's the diagram. This is the MAR or the memory address. And these two, it can be high or low. From here, it decodes the input, then it's increment by 1. From 0 to 0 to 0 to 1, 0 to 0 3 when it is low. Then if it's high, from 4 0, 4 1, 4 2, and so on. And after that, it updates the counter to pass its loaded instruction to the memory data register. After this cycle, let's go to the next cycle itself, called the decoder. The decoder executes the process inputs from the fetch. The decode instruction cycle. Decoder circuit examines the opcode of the instruction. Result selects unique decoder output line. Output line signals is a circuit which implements the corresponding operations. A plus B plus C, A minus B plus C. This is our input. So let's pass it by using the decode instruction cycle. So, in this question, we simply evaluate these given operations. We simply add the letters minus and then we simply get the solution and the final answer from this given question. After you decode the input's number from the French, it executes then run the program itself.
To begin with our discussion about registers, let us define what is register first again. Registers is a hardware device that stores a variety of data about addresses, programs, and such. But other than that, register is a temporary storage. In the CPU, placed at the topmost level of the memory hierarchy, and one of the major designs main object is a register. Address registers are large enough to hold the full address. address reg. In short, address reg. Full address. And for the data registers, it is large enough to hold one word. Data reg. Full one word.
I will discuss the two main roles inside the CPU. There are, number one, user visible register and control and status register. I will discuss under the user visible register. There are general purpose register. General purpose register can be used in variety of ways. They are used within the instruction set in orthogonal or say as a logical connection with the operation. In some cases, this register can be used for addressing function. In other cases, there is a partial or clean separation between data and address register. And the next is data register. Data register is used only to hold data and cannot be employed in the calculation process of a operand address. And address register address register can be recognized as another general purpose register, or they are devoted to a particular addressing mode. Under the address register are segment pointers. The holder of the address of the base of the segment and index register are used for indices addressing, and stack pointer is used to allow implicit addressing, that is push, pop, and other stack instruction need not contain an implicit stack operand. And the last one under the user visible register is condition codes, also known as flags, are bits set by the processor as a result of operation. These are collected in one or more register. They can form a control reg. However, register? Ulitin ko sa pinaka-umpisa. Okay. Ito yung game na.
Game.
Are the bits set by the processor as a result of operation. These are collected in one or more register. They can form a control register. However, programmers can alter them.
So let's move on to control and status register. Control and status register is not visible to user on most machine. However, they can be accessed using the assembly language. Under control and status register, there is There are four essential instruction execution. The first one being the program counter. The second is the instruction decoding register. In short, it is a IR, indicated as IR. The next is the memory address register. Memory address. And the last one being the memory buffer register. Program counter. Program counter contains the address of the instruction to be fetched. The next one is the instruction decoding register. Contains the address of the instruction of the most recently fetched. The next one is the memory address register, which contains the location in memory. The next one and the last one is the memory buffer register. It contains the address of the word of data to be written.
Okay, so now let's proceed to x86. What is x86? It is a family of backward compatible instruction set architectures based on the Intel 8086 CPU and its Intel 8088 variant. The 8088 is actually just a slower version of the 8086 CPU. The 8086 was introduced way back 1978 as a fully 16-bit extension of Intel's 8-based 8080 microprocessor, with memory that can be covered by a plain 16-bit address. The term x86 came into being because of the names of several successors to the Intel's 8086 processor ended in 86, including 80186, 80286, 80386, and the 80486 processors. Now, the history of x86. The x86 architecture was first used for the Intel 8086 Central Processing Unit, released during the 1978. Although not binary compatible, it was designed to allow assembly language programs written for these processors to be mechanically translated into equivalent 8086 assembly. And this actually made tempting software migration for many customers.
This is the overview of x86 architecture. The x86 architecture is a variable instruction length. Primarily is CISC design with emphasis on backward compatibility. The instruction set is not typical CISC, however, but basically an extended version of the simple 8008 and 8080 architectures. And also, byte addressing is enabled when words are stored in memory with little engine byte function. Memory access to online addresses is allowed for all valid word sizes.
We're going to discuss what is pipelining. Pipelining is a technique used in advanced microprocessor where the microprocessor begins executing a second instruction before the first has been completed. A pipeline is a series of stages where some work has been done at each stage. The work is not finished until it has passed through all stages. With pipelining, the computer architecture allows the next instruction to be fetched while the processor is performing arithmetic operations, holding them in a buffer close to the processor until each instruction operation can perform. How pipelines work? Pipeline is divided into segments that can execute an operation. With the other segments. Once it is finished, it will pass through the next segment.
1, 2, 3, go.
Interruptions insert unplanned extra instructions into the instruction stream. The interruption must take effect between instructions. That is, when one instruction has completed and the next has not yet begun. With pipelining, the next instruction has usually begun before the current one has completed. All of these problems must be solved in the context of our need for high-speed performance. If we cannot achieve sufficient speed gain, pipelining may not be worth the cost.
So, yun?
May isa pa. Okay na. Solutions. Possible solutions to the problems. For timing variations, to maximize the speed gain, stages must first be chosen to be as uniform as possible in timing requirements. However, a timing mechanism is needed. A synchronous method could be used, in which a stage is assumed to be complete in a definite number of clock cycles. However, synchronous techniques are generally more efficient. A flag bit or signal line is passed forward to the next stage, indicating when valid data is available. A signal must also be passed back from the next stage when the data has been accepted. In all cases, there must be a buffer register between stages to hold the data. Sometimes, this buffer is expanded to a memory which can hold several data items. Each stage must take care not to accept input data until it is valid, and not to produce output data until there is room in its output buffer. Next, data hazards. To guard against data hazards, it is necessary for each stage to be aware of the operands in use by stages. Further down the pipeline, the type of use must also be known. Since two successive reads do not conflict and should not be caused to slow the pipeline, only when writing is involved is there a possible conflict. The pipeline is typically equipped with a small associative check memory which can store the address and operations type for each instruction currently in the pipe. The concept of address must be extended to identify registers, as well as each instruction can affect only a small number of operands, but indirect effects of addressing must not be neglected. Branching. One solution which is widely used, especially in RISC architectures, is deferred branching. In this method, the instruction set is designed so that after a conditional branch instruction, the next instruction in sequence is always executed, and then the branch is taken. Thus, every branch must be followed by one instruction which logically precedes it and is to be executed in all cases. This gives the pipeline some breathing room. If necessary, this instruction can be non-op, but frequent use of no-ops would destroy the speed benefit. Interruptions. The fastest but most costly solution to the interruption problem would be to include, as part of the saved hardware state of the CPU, the complete contents of the pipeline, so that all instructions may be restored to their original state in the pipeline. The strategy is too expensive in other ways and is not practical. The simplest solution is to wait until all instructions in the pipeline complete. That is, flush the pipeline from the starting point before admitting the interrupt sequence. If interruptions are frequent, this would greatly slow down the pipeline. Moreover, critical interruptions would be delayed. A compromise solution identifies a point of no return, the point of the pipe at which instructions may first perform an irreversible action such as storing operands. Instructions which have passed this point are allowed to complete, while instructions that have not reached this point are cancelled. Thank you very much.
Now, I'll be discussing about the finite state machine, or FSM. There are two different types of finite state machine, which is correspond to two different definitions of the output function H. The first one is more finite state machine. Representation of JK flip-flop. The circles represent the two states of the flip-flop, we have a label A and B. The output Q is indicate a bracket, which is 0 and 1. And the arcs illustrates the transition between the states. This is the arcs. This is the more finite state. One is the milli-finite state machine, which is consists of circle for each states. A and B are the states. The circles are connected by arcs. For each transition, each associates an output with each transition. Alright. Outputs 1, 1, 1, then 0, 1, 0, and 1, 1, 1. This is the milli-finite state machine. F stands for next state function, and H stands for output function.